Okay, so welcome everyone to this new episode of EagleFly, the experimental debugger. Um, Today we will continue on the process of making this debugger, and you know, I have I need to grab my lenses because they are a mess for me. All right, so yeah, now I feel ready to do this. So yeah, let's dig into the code and see what we can do today. I've already opened it. I haven't done anything yet since the last time we streamed. So the first thing that I would like to do there's two choices. There's two ways that we can proceed with this code construction. One can be the last thing that we did was we got this exception. We set this breakpoint at the starting at the entry point for the process, which is not the entry point for that we expect. That's the if we go to the, which is not the entry point for the application, but it's more for the entry point for the process. So it's totally different. Test debug target. So right now we have this is not the entry point at all, but something like I don't remember, it was this one. It was externcy in main 0 runtime startup in this case, but it can be called anything. It can be called, it depends. Since this is a console application, it's this. Well, it's a C++ thing, but if it's a Windows application, it's gonna be something else. I think it's Win32 main or something like that. With main. And I'm sorry if I sometimes talk Spanglish or say something in Spanish. Forgive me. I would say it in English so you guys can understand. But whatever. Okay, so there's two routes. We can continue on this, like trying to see more implementation cases. Just to see how all these, how are we gonna use this thing, because this is like kind of a starting point. And the other route could be to start to define what we could see as I would like to just to specify. We don't have to do it right now, but I just want to see it, so let me see. We have this debug update tracer, which yesterday we succeeded on serializing it and putting it onto the main loop, which is really cool. So that so in that way we know that everything has an order, and it's kind of it's predictable how it's going to be working. We don't have any kind of crazy stuff going, multi-threading stuff, which is what we want. So now we just have two threads, of course, one for our debugger and one for the new process that's running. And that's really important, because if you think about it, the last time, yesterday, I guess, I don't know if I close this Milton. Let me go and see if I can find it back. So oh yeah, for example, we had this kind of architectural image for the system, and one thing that we were thinking on is like, well, we could try to do some kind of a draw and input demand, which is pretty much is specifically for performance concerns and for like getting the less performance hiccup or hitchcup for the process itself. But one thing that I would like to mention here is that probably it's not necessary at all, because I mean, even though we know that it's like running every time, and probably we're going to render it like if it was like a loop style thing, which I mean, it's okay with, because we know that the process itself, you know, I mean, this is a tracer, and if we go if we go a little bit here, so here's the tracer going in one thread, and this is another, and here's another, and this is another thread going for the process, you know. So the process is not gonna be anytime concerned about the I mean, it's not gonna be ever be super performant just because we're having this thread just running through a loop, you know. I mean, that's not the case. So if this is the target, this target is just free to do the things whatever he wants, and be on its own responsibility to what the performance of itself is going to do. Ourselves, we're going to try, of course, to have this loop being the most efficient and fast possible, so that we have I mean, it's just like the basic things, you know, for an application to be running. And of course, I mean, of course, we have like these kind of locking steps where we will always be like interrupting the target application, you know. So we will always like, hey, you know, stop here and then continue, stop here. I mean, that's the main point, you know. So so for performance accounts, I don't think it's really important to change that kind of architectural point of view for the render itself, you know. So I mean, it's not such a deal to have it that way, and I think it's super even it's gonna be I think good to keep it the way that we have right now. And yeah, I mean, the target's independent for us, you know. The target's gonna, we just receive messages from it, we dispatch it as whenever we need it to, and whenever we pass through the through the tracer, you know, and that's all. That's all she said. And yeah, so the thing that I was like thinking, and the thing that I was like the other thing that we could try to do is to start to see how does the debug manager could work itself, you know. Although I think it's a little bit premature, because we don't have pretty much a lot of information right now. So yeah, I don't think we are gonna do that. So while I was talking, I realized that yeah, you know, let's continue to expanding the usage code here and see what else we would do for the tracer, you know. So for example, Win32 get handle from ID. Well, first of all, it's gonna the debug update tracer is gonna start to run the process. Right now we don't have any kind of pretty much it's like really simple. Just starts the process and it's gonna run it once. If it finishes, it's not gonna run it any more time, and it's gonna, if we set a breakpoint, we could stop it in there, and that's all we got, you know. We set a breakpoint here, you know. We minimize the instruction pointer 1 byte, because we know that's how it works. And we could at this moment see if we can, for example, we say that we display this stuff here for the registers, and we let me compile so we can see. For example, one thing that we will assume is that whenever we cross through here, we have the breakpoint count for the process. So whenever we run it, we know that we have like indexing, you know, to the it's like a pretty simple thing. Like we just whenever we encounter some breakpoint, we advance the breakpoint index, and we found the last one, you know, we reset it to 1 because we know that well, it always will start with 1 because we know that there's a invisible pointer like in Windows stuff and stuff like that, you know? Which I don't know if we can. I mean, we can not. We can start from 0, I guess, but and I don't know, do the same stuff, I guess. But it doesn't matter. It doesn't matter. So let me see. So if we run this, let me see what we got. And there you go. The first one is create process, and I think as well you won't see this, but it's kind of crazy. How can I do this? Because my window is so little. Well, okay, I wanna first press F5. We process it. We have the window there. We created the process, and we can see its handles, everything going on there. Then some DLL is gonna be loaded. Another DLL is gonna be loaded. Oh my god. Please, Visual Studio, don't crash. There you go. Another DLL, another DLL, and this is the first exception, which we don't care much because it's from Windows and it's like pure symbolic thing, I guess. It's like, hey, now's your turn, man. Do your stuff or something. I don't know. So it doesn't matter. And then we have the second breakpoint, which we handle it. And the thing that says like, hey man, we don't want to continue tracing because it's a breakpoint. And we want to reset the function the function pointer, the instruction pointer, sorry. And we're gonna write all this stuff. That's basically the registers allocation. So at that point we're gonna see that those are the registers, and those are the values for the registers. And then we say, hey, please return the context to the place that I told you to do, and continue. So I will write the data back with the original code back that we take care. Oh, I'm sorry. With the code that we set on the process creation stuff, which right now we just have it there because we don't know. And we flush the cache and advance the pointer, and they set to 0. We break. It's not gonna be traced, and we continue with the normal stuff. We can go to F5, and there you go. So right now, what this thing is going, the process itself is being paused. It's totally stalled. We have a breakpoint in it, and the update itself, it's running happily in its own thread, you know, which is exactly what we want. So now I would like to and if you think about it, we don't have we haven't processed since we okay, well, those are not ours. Yeah, so probably we want to do something with it, but for now it's okay. What I was saying is that if you see, since we set a breakpoint, we don't have a way to continue. That's the first one, and we are not we haven't seen the output of the string that we had before, because we had the instruction pointer haven't got that yet. So yeah, and we know that everything else is going on good, you know. So we can try to display as much code as we could, I guess. For example, right now we have the registers, but what if we want the call stack or stuff like that? We could try to get the call stack itself. Which I believe, and this is where things gonna go crazy. We can go and dump the call stack. That would be something good to do, I believe. Or we can like trying to find a way to inject input code and resume the thread, for example. Which, I mean, that's something simple to do. Which could be probably like something like this. And the exception single step, I don't know what's that for. Let me see. I have to take a look a little bit more into exception stuff, because it apparently seems to be the bread and butter for debugging stuff. Let me close all this stuff. We don't care too much about it. I don't care about that. Although that, well, I don't remember, but and here's where the interesting part comes, for example, because I mean, one way we could do it, if we want to display stuff, that's like where we are at right now. So we are like in the moment. I mean, we set a breakpoint, and like in the normal case, for the user, like what the user wanna see, for example, if we step a breakpoint, I don't know, like right here, you know, we step a breakpoint, we run, and I believe I thought, did we erase all the breakpoints? Probably it's not compile, I guess. Probably it's not compile. So you see, it's like I don't know how Visual Studio works, but I mean, one way that we can do it is that when the breakpoint gets set, you know, the process is running, we get to the point, and then we can start like this kind of displaying stuff, you know. That can be one route. Or uh, as a callback per se, or we could try for example this watch window. It's something that it persists, so it's something that we write itself, so we can see the context. So I mean, there's some kind of a state here, you know. So there's some kind of a state of variables, some state of the code, some state of the code stack, some state of uh, the registers, the memory, the registers. So everything has a state on a specific moment, you know. For example, we stop here and then boom, the whole stack it gets displayed, you know, in everything with different contexts, you know. So it's like a lot of stuff gets displayed whenever we stop, you know, because there's a lot of data. A lot of data gets passed in process, and the process itself. I mean, if for example here we have a step over, and a step over is gonna tell you, hey, these things change, these things come from registers. These registers change its value. The memory at some place changes value also. The threads, well, the threads are just the threads, I guess. This is the call stack. This is the call stack. These are the modules that got loaded into it. Sure, a lot, guess. A lot. So imagine, I mean, all these things have to be loaded. If you see, I mean, these are all DLLs. I mean, all the things that we see in the output stuff basically are DLL stuff.
I'm always serious.
What? Forget it. And then we have temp DLL, it was loaded, cannot find or open the PDB. So it loads the PDB also for those symbols, because if you, well, yeah, so Visual Studio uses the PDB itself to load the symbols, which I don't know if we want to. I mean, that's one route to get it. I mean, for getting the call stack, that can be one route, you know. So we can do something like Well, before going the route, I guess from the PDB, I would like to try a way to step over, like a single step execution. So that was the thing I was looking for. So we can go like step by step running the process, So let me see. Well, if you think about it, we can do it ourselves, isn't it? I don't know if we need to pass it to a single step. I mean, but I have an idea of how we can do it ourselves. Because if you think about it, we have the context, so we can move pretty trivially. Well, we don't know the size of the instruction itself, so that's kind of crazy. So how to get the size of next instruction? What? I can see the disassembly. There you go. So these are the code bytes. So these are the line numbers, but that's not representative of the assembly. So basically what we like to see is basically all this stuff, you know, a list of all this stuff. I think that would be really nice, you know, to have like the assembly being done for each instruction, like a dump bin or something like that. So for that we'll need to get to the, I don't know if it's in the binary. Well, in the binary it's everything, but I was like, I mean, how to reconstruct these instruction paths. I don't know if in the PDB itself it's in, or let me see. x86 has an instruction reference time. I need x64. You can use Intel's, which I believe we got it here. So we have a data cache. I mean, I think we should read this because this is gonna be kind of a good backup, because if we try to understand a little bit more of how this the Intel x64 processor works, we can make ourselves this kind of stuff, because even though, I mean, this is like really really processor specific, it's gonna help in the general terms. 32k instruction cache and 32k write back data cache. Has branch prediction, data prefetch logic, support for MMX track, MMX, SIMD, and SSC2. So yeah, I mean this is like the whole thing, yeah. It can decode, dispatch, and complete execution of 3 instructions per clock cycle. That supports out of order instruction execution. And you know, I mean, this is the kind of thing that I want to be concerned about, because I mean, from the outside it seems kind of simple, you know, like advance to the next instruction, but you don't know what's the next instruction, and that was the reason that I wanted to focus on looking at how the 686 the x64 did it, and I mean, how can we get the next instruction itself, you know. I mean, I probably, and I guess, I mean, somebody asked like, why don't you use Windows way to use it? I mean, probably we're gonna use it, but the thing is, like, I want to understand how it all works, you know, so that we are not catched with, oh yeah, this is the thing we works, but we don't really understand how it works, so get caught by the uncertainty. Oh, cool. So there's a system bus that goes all the way around. So there's the first level cache with 4-way low latency, and it connects directly to the second level cache on die in an 8-way, and it also connects with the execution for the core, which retards the instruction, I guess, and then it goes to the branch prediction, and then it fetches the next instruction and it decodes it somewhere. Okay, fetching the codes is here. Okay, fetch the code and then it passes on. Oh, okay, so it can like opt not to do the fetch the code thing and go directly to the execution instruction cache microcover and ROM. And this is like, okay, so this is like this kind of advanced transfer because you can choose not to go to second level cache, and it keeps itself on instruction cache on this kind of in this kind of cycle, you know, that it goes hey and then it goes back on the same, because if he had because if it goes from the second level cache, it has another connection to the fetch decode, so it can go back into here, or it can go from the second level cache to the first level cache, which okay. And if it's not here, it will go to the bus and find it on the third level cache if it was, or to memory. Okay. Allows the processor to decode instructions beyond branches. So it's gonna grab from wherever, you know. Like this branch, I don't care which branch it is, it's gonna boom, grab it and process it. And then yeah, it has it. Oh Jesus, it has the dynamic data from flow analysis. I mean, it's the one that basically sees the dependencies across the instructions, so it can take as much as from out of order instructions as it can. The out of order instruction execution core can monitor many instructions and many instructions. Okay, many is not a number, man. Can you tell me how many? In the order that base optimizes the use of the processor's multiple execution units while maintaining the data integrity. Cool. speculative execution refers to the processor's ability to execute instructions that lie beyond a condition of branch that has not yet been resolved, and ultimately to commit the results in the order of the original instruction chain. To make speculative execution possible, the basic processor architecture couples the dispatch and execution of instructions from the commitment of results. Okay. Okay, so yeah, that's important because if you want to predict, you don't know how was the stream, so you just want to. It's like if you wanted to resolve all the whole things, but since you know how was the order, you will reorder when you got that the branch was correct, um, and you like reorder the whole data results, you know. So it has to be like really since it has like this kind of branch prediction and speculative execution, you can do that kind of stuff. So it's gonna do, since it has speculative, it's gonna put it in some cache way, you know. It has to have some kind of place to dump the results, and then some way it's gonna reorder it whenever he knows that it's the right branch to execute. Okay, so it stores them on registers. So the return unit linearly stretches the instruction pool for completing instructions that no longer have data dependencies with other instructions or unresolved branch predictions. When completed instructions are found, the return unit commits the results of these instructions to memory and or the IFA to the registers. basic integer operations can dispatch in 1 half processor clock tick. So there would be like get dispatch in a half the time of a clock tick. The Intel NetBurst microarchitecture is really similar to the one, the Pentium one, but this has a thread level before the bus unit, and it has this microcode run. No, this is the same. But this is the same. What's the difference? And it doesn't have any connection here, which it was it's a little bit simpler. The front end PAM line okay, so this is the beginning. Ah, oh, there you go. Memory, the address space, general purpose data registers, segment registers, the flag registers, and the instruction pointer register, which is basically all this data that we have here. Yeah, all these things that we have on the context itself, we can make sense of it whenever we get it. applications access only the first 4 GB of linear address space. Like protected mode, this mode allows applications to access physical memory greater than 4 GB using PA, physical address extensions, PAE. Oh, okay. So those things that we were looking at, like the W and D, were the size override prefix. Well, in those cases they were like suffixes, but I guess it's the same. You can put whatever you want, I guess. So you have like, if you use those prefixes, you can specify the size for the operation codes, for the opcode. And if you have the rex sections extensions for the prefix, you can modify the registers themselves. A program or task running on an IL-32 processor is given a set of resources for executing instructions and for storing code, data, and state information. Exactly, it's state information. The resources described briefly in the following paragraphs and shown in Figure 3.1 make up the basic execution environment for an i32 processor. An Intel 64 processor supports the basic execution environment of an i32 processor and a similar environment under i32E mode that can execute 64-bit programs and 32-bit programs. The basic execution environment is used generally by the application programs and by the operating system or executive brain. So there's a physical address space of up to 64 gigabytes. Well, that probably is because they have to support these kind of big memory sizes, you know. And then you have the basic program execution registers. We have 8. So they can work, these basic execution registers work on bytes, on words, on double words, and that's all. Because that's the size for, they are 32-bit size, see? Yeah. Well, some of them are like 64 bits. 64 bytes, sorry. 64 bits. So the floating point unit has it basically has like it has like the same kind of, it has registers. It has 8 registers. It has some status register and a control flow register. It has its own instruction pointer. So that means that basically there are like 2 sets of instructions for each ALU. One from the ALU and the other is from the FPU. And each one it's like in its own instruction pointer handling their own separate set of instructions at its own time. So you can be processing like a floating point 1 and integer 1 simultaneously, I'll assume. Double extended precision. That can be like, I don't know, like 128. And you can also process integers in binary coded decimal value. So for MMX they are 64-bit size, but they work differently. I mean, if you think about it, yeah, it should be like, I mean, these two technologies have to be totally different, you know, because MMX works as a pack thing, and FPU registers work as a specifically to handle floating point precision operations, which we will understand them in a minute, or probably more, but it just we will still understand them later. Okay. And the difference between MMX and XMMM is that XMMM can process floating point operations. And on 128, and it's 128 bits, you know. So it can work on 32 on floating point on single precision and double precision ones, and it can work also for the pack work, double work, and quad work integers. And the YMM registers support 256 bits in the operations and 250 pack single precision, double precision floating point values, and a 250 pack word, double word, and quad word. Alright, so it's like getting bigger, you know. All is getting bigger here, you know. Each of the bound 0, bound 3 registers, so there are 4, stores the lower and upper bounds 64 bits each, associated with the pointer to memory buffer. They support execution of the Intel MPX instructions. MPX. So they store like pointers, basically. Oh, to memory buffer. Oh, okay, so it marks like arena or something, or a buffer basically. So it's like oh right, okay. So okay. So we have a bounds there. I mean, we know what bounds. We can define an area, a memory arena or a memory area in which we designate data, for example. And we can work on that. Okay, so also okay, that's crazy. Because I mean, if I understand correctly, well, no, I mean, you cannot, you don't just manipulate registers and what I mean, you manipulate registers and with these host sizes, but you can manipulate bounds of memory in which you like are like processing, you know. I don't see the MPX instructions, but they should be somewhere here. Well, I don't know. Doesn't matter. So we have this the bound configuration, configure user mode MPX operations, and on bound checking, and bound status provides additional information on the hashtag BR caused caused by an MPX operation. Okay, so there's some kind of bounds working there. You know, we can work on boundaries, you know, of memory space. And then We got basic program execution register. Okay, this is the whole thing. This is the whole picture for non-64 bit modes. Okay, so this is the area 32 for non-64 bit modes, which is basically we have an address space from 0 to 232. That's for 4 gigs of address space. And it can be flat or segmented, which I don't know what it is, but well, I guess segmented is just like it segments each one in pieces, I guess, or it's just like boom, the whole thing. And you can use the physical address extension mechanism. A physical address space of 236 can be addressed. But I mean, just to be sure, because the address space itself, it's I mean, virtual memory, it's an OS specific thing, you know. I mean, here we are not talking about virtual memory. This is all physical memory itself. So this is physical memory, and in physical address space, we can be flat or segmented, and we can have address extensions to that lets us to map memory to up to 236 to 236 power minus 1, and yeah, using PAE. Okay, that's for memory. Then we have the basic program execution registers. We have 8 32-bit registers. We have 6 16-bit registers. And then we have 32 bits, one register for 32 bits, that's the EagleFly register. And we have a instruction pointer, that's another 32 bits. And the segment registers are 16 bits. This is kind of interesting. It's interesting. And that's for basic things. Then we have the FPU unit, which has its own registers. That's it has 8 80-bit registers. Okay, so they are 80 bit. Why that are 80 bit? And they are we have 3, one for the control, status, and the tag register. We have an operation code register. It's an 11 bits, so it's about like a 91. Man, this is all crazy. But you know, with floating point, I think that's the way it works, because it has to be working for mantisas, extension exponents, and the sign, I guess. I don't know. FP instruction pointer register, which is a 48-bit, and the difference is this is 32 and this is 48. And this is a data operand pointer register for the operand. Then we have MMX registers. No, sorry, please stop. I don't need your help right now. We have the MMX, XMMM, YMMM. Plus 32-bit MXCSR, and we have a YMMM register, 8 YMMM registers of 256, and then we have a bounce register that's there are 4 bounce registers, each of 128, and each one has a register that's a bounce configuration and bounce status. Cool. And here's the cool part. To support procedure or subroutine calls and the passing of parameters between procedures, the stack is located in memory, section 6.2. Stacks for more information about stack structure. In addition to the resources provided in the base execution environment, the IL32 architecture provides the following resources as part of its system-level architecture. So we don't have I/O ports being explained thoroughly here. So we process I/O ports. So it allows us to process and transfer data from one input to output. In the Intel blah 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 64 and IL32 software developers manual volume 3A. I don't know which volume this is. This is volume 1. This is the volume 3. And we have, I don't know where's the A. Man, why am I like zooming on like crazy? I don't know. Dude, it moved me. Oh, I hate this. I think I'm gonna find another application for reading PDFs because this doesn't do the thing that I want. Okay. For more information about stack structure, in addition to resources providing the basic execution environment, the authority practice blah 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 provides the following resources as part of its system-level architecture. We have control registers that are for the operating mode of the processor. Which is in some other volume. Memory management registers. have debug registers DR0 through DR7. So we have some debug registers which we can use. The performance monitoring counters allow processor performance events to be monitored. See Chapter 18 Performance Monitoring in the Intel 64 and IA32 architectures. Managing the state using the Xsave feature set. Okay, so this is cool. Procedure calls, interrupts, and exceptions. Oh, okay. This is cool. Okay. So we are here. Okay, so I think that I'm gonna stop here because yeah, we have a way to go for looking at the IA32 and 64 architectures. Which um, it's the canonical thing. It's just like the thing that we should know to really understand how to move data up and down from uh, and to basically, I mean, if we, especially for the debugger that's basically really working on instructions and how machine code it's operating, so this is like the essential things. So yeah, okay, so we will continue this on the next stream. For now, I would like to say, please, if you have any questions of what we did today, you can ask them on Twitch, on Twitter, or on YouTube, and I'll be happy to answer them. So yeah, for today that will be all. There was no coding today, but it's alright. We have a way to go, and we will continue up on the next stream. That's it. I will see you all on the next stream.